Okay, we should be live. Welcome to another session of our reading group on the assumptions of physics. We will wait for a minute for other people to join, and I will, as usual, let's see if I can remember to share the link and share the screen for people who want to follow along. So share, and this is everything. Okay, promote to panelist. And I think I am set. Okay, so last time we looked at full kinematic equivalence and we were able to recover the equations for massive particle under scalar and vector potential fields. And today we are gonna basically move to the extended phase space. And actually, no, we were already in the extended phase space last time, I think. Uh, and no, last time we were not in the extended phase space, right? We just had position and momentum. And today we're going to extend the phase space with both time and energy and see that basically to make everything work with coordinate transformation that includes time, you basically start having a similar structure that you would have in relativity. There are going to be a lot of things that are going to remind us of relativity. So we should start. Artem, why don't you start?
In this section, we analyze what happens if we consider a change of coordinates that mix space and time. We will see that relativistic elements appear even if a notion of metric tensor is not introduced and the particle-antiparticle duality emerges. Moreover, under the full kinematic equivalence, special relativity is recovered.
Hamiltonian mechanics on the extended phase space. The Hamiltonian formalism is invariant under generic change of spatial variables. But if we want to introduce generic changes of variables that mix space and time, we have a problem. In the standard formulation, time is the parameter of the evolution, qi as a function of t, meaning that we can mix the spatial variables while leaving t alone. In the formulation extended by time, time has a double role of parameter and variable. That is, we write qi of t and t as a function of t. Therefore, mixing qi with t will affect the evolution parameter as well. What we need to do is to separate the time variable from the parameter of the evolution. We can group the spacetime variables as q alpha, which is just t and then appended qi. We introduce an affine parameter s, and therefore a trajectory in spacetime will be noted as q alpha of s. Under a change of coordinate, the variables q alpha will mix, but the affine parameter s will not change.
Now we have understood how to deal with time, we have to understand how to deal with energy. As we saw before, the Hamiltonian is no longer invariant under transformations that affect time. Moreover, even if we start with a time-independent Hamiltonian, it will not remain so under a generic coordinate transformation that mixes time and space. This means that during the evolution, energy will not be constant, but will need to increase and decrease. Another more physical way to look at it is that energy, like momentum, is not an absolute quantity, but rather a relative quantity with respect to an observer. If we imagine an observer that is accelerating and decelerating in the same way that he will see momentum change, he will see the energy change as well. In the same way that momentum is sensitive to changes of units along the corresponding spatial direction, energy is sensitive to change of time units. To be able to characterize these relationships better, we introduce an energy variable E, which we group with momentum variables, and since minus the Hamiltonian was the time component of the potential theta A, we write P alpha minus energy and the momentum, so that P alpha is a covector.
Okay, question from Ian from the chat. What does it mean to say that the parameter S is affine? And so in this case, affine parameter just means that it's a parameter of the curve. I don't think it has any relationship to affine transformation and anything like that. It's just the term that I've always seen used. So it's just a parameter for the curve.
Is the square brackets just for like vector?
Yeah, it's just the grouping for the vector, yes.
Okay.
And I quite never understand whether I should put a comma there or not. Probably I shouldn't, because it's just a vector, and the vector doesn't you don't it's not comma separated. I always get
There are
confused with the
different
notation.
conventions. Yeah.
Oh, there are different conventions, so it's not that I get confused, it's that I read books that do one thing and other books that do another.
Yeah, I think there are like I know that in school when we touched vectors, we always had components vector separated, but I don't know. I'm in Ukraine, so it might be.
Yes. Well, I was from Italy, and I've learned that for example that inner product sometimes in Italian is also called the scalar product, and
Yeah,
that's
same for
not.
us.
Same for you. In the US, no, you should call it inner product, not scalar product. So anyway, yeah.
So is pi the like 3 momentum?
Correct. It's the
Okay.
momentum for the direction of um, for each of the spatial direction. Well, I mean, Q technical could also be not space, could be everything. So
Okay.
I think you need to promote Julius to panelist as well.
I think I did, but he can also, like, if he doesn't want to use the video, he can also. Oh, but I need to at least allow to talk. I see. Okay. Interesting. No, now he's a panelist. Okay, good.
Yeah. Hello, everyone. Thanks for
Hi,
adding.
Julius.
Hello.
Hi.
You can read next, Julius.
Okay, where did we stop? Okay, what we did is add a temporal degree of freedom, and with that addition, the equations look a lot like standard Hamiltonian mechanics for multiple degrees of freedom. We have, yes, so we have this canonical, yeah.
Yeah.
And then we define the potential theta A and the form omega
AB.
AB such that yeah, the equations hold, and then the equations of motion will be yeah
SA omega AB equal partial BH.
yes, okay. So the function h is called the Hamiltonian constraint. Typically, the constraint is chosen such that h is equal to 0.
Yes. So we'll see later, like an example, so that you guys can see what it is. But the point is that when we are adding time like this, like everything seems, seems to work in the same way. Hello to regular shorts. Somebody else new. Good. There are more people online today, which is fun. I don't know what happened, but good.
Okay, so a relativistic free particle. Given that this formulation is probably unfamiliar to most, let us see how it works for a free particle in a Cartesian and inertial reference frame. In this case, it is more convenient to use Q0 equals Ct as the time variable, which given in 1.110 means P0 equals minus E divided by C for the energy. The Hamiltonian constraint is
Okay, so this is essentially a 1 over 2m. This P alpha, P beta is contracted with the metric, the Minkowski metric, as I said here. So this is basically the norm of the form momentum. And then you're summing just m square c square. And then if you expand this, is just going to be the norm of the spatial momentum minus the energy over c square plus mc square c square. So if one is done relativity, should kind of recognize this, right? You're just basically saying that the norm of the form momentum, like if you imagine that you're setting this equal to 0, then you're basically saying that the norm of the form momentum is going to be MC. Right? That's essentially the only thing that this is saying.
Can I ask a question?
Yes, go ahead.
Yeah, regarding this metric, because in the previous lecture we had this, let's say, metric tensor, but it was just an assumption that the derivative depends on the point, and it's that's why it's two-indexed object matrix, maybe symmetric matrix, but we do not connect directly to geometry. And now here this eta is the same question, like do we assume something, or how does it come here?
So this is just an example. So this is not a general thing. It's just to give you a sense of what this H is going to end up being. What's going to happen is that later there's going to be a similar procedure, right? So if you impose that you have a linear relationship before the form momentum and the form velocity, you're going to get the same thing that we had before, where, well, we don't know that this is a metric tensor. We just comes out from the linear relationship. So right now we're basically just I'm giving you the example for the Hamiltonian constraint for a free particle, so that we can get a feeling of how the math works. Does that make sense?
Yes. If it's an example, then okay.
Yeah, it's just an example. And then there is a question, I have a general question, maybe in relation to the exactly, can we add a fifth component of form momentum as a mass? So in principle here, we are just doing what the Q's and the P's are. It's completely left specified. You can have as many as you want. The assumptions don't change. The time and energy, though, are special. Like those are just one. Those we can't add as many as we want. Okay. Okay, so let's go through the equation. I'll just talk over them at this point. So if we now use the Hamilton's equation that we have defined before, you have the derivative in time of Q0, which we said for this specific example, we're just going to use a CT, right? This derivative is going to be the derivative of P0 with respect to P0 of the Hamiltonian constraint. So it's going to be the derivative P0, we said it's minus E over C. So we are taking the derivative of all of this with respect to minus E over C, which is essentially just this term. So we have 1 over m, then the derivative of this term, and then it's the derivative of something square. So this is just minus 2 minus EC. And so we do it, and we just get that the derivative of CT is E over C over m. And so the derivative in time with respect to the affine parameter is going to be E over mc squared. So the energy over mc squared. And we can do the same for the derivative of space with respect to the affine parameter. So you get the parcel H with respect to the momentum. And again, this is the only part that depends on the momentum. And so what you get is the usual derivative of p squared, which is just p. And so the derivative, the velocity is going to be pi over m. Then we can do the derivative of p0, which is the derivative of the energy. And the derivative of the energy with respect to Q0, right? With respect of the derivative of the Hamiltonian constraint with respect to Q0. The Hamiltonian constraint does not depend on Q0. So it's this is 0, which just means energy is conserved. And then we can change the derivative of the momentum, which is the derivative of the Hamiltonian constraint with respect to QIs. This does not depend on the QI, and so this it remains a constant. And again, so what you have here is that the derivative of the position with respect to S, that's going to be the force velocity, right? So the relationships that we have here is essentially that the force momentum is equal m the force velocity. And then I don't know who was reading, can continue reading.
Okay. We recognize u alpha as the force velocity and the affine parameter S as proper time. With this in mind, we can rewrite the Hamiltonian constraint as we just rewrite the moment as mass times the force velocity, right?
Mm-hmm. Yes.
Okay. Which looks like a kinetic energy term constructed from the force velocity. Setting h to 0 then means setting the norm squared of the force velocity to minus c squared, which is consistent with special relativity. It also means that minus e over c squared is equal to m squared c squared plus the that would be the norm for the 3 momentum.
Yeah.
And we have the familiar formula for energy. That is, the Hamiltonian constraint sets the relationship between energy and momentum.
So the point of all of this should be, if you have never seen this done like this, it's a much better way to do Hamiltonian mechanics in relativistic term. Like typically what people do, and I don't know why, because this is like from the 40s, like this is not something that I came up with or somebody recent came up with this idea of using the Hamiltonian constraint. But typically in a lot of relativity textbook, you still use the Hamiltonian, that is the conjugate of time. And that's why you have an ugly Hamiltonian with the square root, essentially. But if you do it with the Hamiltonian constraint, everything is quadratic and everything like, it's exactly as you would expect by generalizing the equation. So.
Yeah, I have a question.
Go ahead.
You mentioned here that affine parameter S works as a proper time. And proper time is a special variable. It's not like a coordinate variable in the sense
Correct.
that it's, and here it is presented in, well, it does not reveal that it is actually invariant way of, how to say, tracking how the object is moving. So this we'll also see later, or how should we take this?
I don't know if I talk about it later, but it comes from the definition of a Hamiltonian constraint. So the fact that S is the proper time is exactly because we chose the Hamiltonian constraint in this form. If you could change the Hamiltonian constraint, you can change the expression, right? And get something that it's not proper time. So I think we're gonna see that later, or at least mention. But the point is that the S is special, proper time is special. Precisely because it's let's say the conjugate of the Hamiltonian constraint, which is an invariant not just under coordinate transformation, but it's also conserved in time. So you get this relationship between this, and you can see that the Hamiltonian constraint is essentially kinetic velocity. And so in a sense, you have this correspondence between proper time and the kinetic velocity.
Mm-hmm. Yeah, it is.
Kinetic energy, sorry, not velocity. It's kinetic energy.
Yeah, it is interesting because I never like looked at it from the point of view of like dynamical systems and Hamiltonian flows. So it is a different way. Yes.
Exactly.
Okay.
Yeah, that's exactly it.
Interesting. Okay, thank you.
And Ian mentioned that a lot of the methods used in this example were also used by, so the methods used here are absolutely standard. There is nothing here that I made up. It's just that I don't know why it's not included in more like basic textbooks of relativity, and it's not taught as much. I never understand how which topics get popular that then get taught and which aren't. So
Sorry, this is a comment regarding this Hamiltonian formulation.
yeah. So
yes.
it was a comment from
Mm-hmm.
a question from the chat. Okay,
Yeah, I think these methods are more popular in how to say relativistic gas formulation when I think if you remember some time ago I sent you a letter with a couple of articles about phase space approach to relativistic gas and charged particles, charged gases. There it is more apparent that this is needed. In standard relativity is not really a popular way to teach.
Yeah, I would think that if you're doing statistical mechanics, this would be much easier to treat.
Yes, that's what they do indeed. Okay, so I guess I can take over here. Yeah. Okay, the geometry of extended phase space. Note that while the mathematical structure of the extended phase space looks the same at the first glance as one of the standard phase space, it has important differences. Let's concentrate on the Hamiltonian constraint. In the standard Hamiltonian mechanics, the Hamiltonian H gives a value of energy that is conserved by the system during the evolution, but the system can be in different states with different energy. The Hamiltonian constraint H, instead, is a quantity that is not only conserved by the system during the evolution, it is always the same for the given system. In the example above, the Hamiltonian constraint essentially is a constraint on the mass of the system. Therefore, the space of states is not really the full 2n plus 2 dimensional manifold charted by time, position, energy, and momentum, but it is in the 2n plus 1 dimensional submanifold that is given by the constraint h equals to 0. The constraint lowers the dimensionality by imposing a relationship between energy and the other state variables. The Hamiltonian constraint then plays a double role as a generator of the evolution over the affine parameter S and as an equation of state of the system. Yes, note that to apply the constraint to a distribution rho, one can simply write h rho equals 0. This means that rho can be different from 0 only over the region where h is 0, and therefore rho is non-zero only for those points that satisfy the Hamiltonian constraint. Moreover, note that in the case of a free particle in Cartesian frame, the Hamiltonian constraint h rho equals 0 is the classical analog of the Klein-Gordon equation. Yes. Klein-Gordon, yeah.
Right. So the point is that you should see the analogy by Hamiltonian constraint applied to the distribution equals 0 to the Klein-Gordon operator applied to the wave function or the field equal to 0, right? That it's clearly that there's something very similar going on there.
Okay, I wonder if you have looked at this different formulation of classical mechanics developed by van Neumann. It is where it is made as closely, well, it is made to look as closely as possible to quantum mechanics without actually being quantum mechanics.
Where you basically use the square root of the probability as the state?
Probably, I have to revisit, but
yeah, so
yes,
there is that it has a name that I always forget. It's the joint name of two people, and
it's something
so
like Koopman von Neumann or something like
yes,
that.
something like that. Yes, yeah.
Okay. Okay, let's get back.
Right, Alina?
Okay.
Right. Since over balanced states we will have both h equals 0 and e equals h, we can write h equals lambda h minus e, where lambda is a function of the extended phase space. This expression provides a link between the Hamiltonian constraint and the standard Hamiltonian. To understand what lambda is, know that it equates ds, so that's the affine parameter. So dst equals partial minus e of h equals lambda. Therefore, lambda is the rate of change between time and the affine parameter. Additionally, given that time must still be a possible parameter for the evolution, t of s must be an invertible, strictly monotonic function. Okay. Therefore, we must always have dst different from 0, at least over the region where e equals h. We can now verify that the new formulation recovers the old in equation 1.141.
Okay, so I'll go through this. So we said the Hamiltonian constraint in principle I should be able to write it as this lambda h minus e equals 0. So by inverting this, I know that E is going to be equal to H. So that the energy is going to be equal to the Hamiltonian, where the Hamiltonian is a function of position, momentum, and time. And then you start writing, you want to say that the derivative of time with respect to time is 1. And since time and the affine parameter must be invertible, then you just have the derivative of the affine parameter with respect to time. Multiplied is the inverse of the derivative of time with respect to the affine parameter. So these are going to be 1. And then use the Hamilton's equation on this side so that you have the partial E over H, and you get the lambda here. So that the derivative of the affine parameter with respect to time is 1 over lambda. And now you can express all the derivatives of all the other things in time by using the chain rule as derivative of affine parameter with respect to time and derivative of the quantity with respect to the affine parameter. Then you use a derivative of affine parameters with respect to the affine parameter with the equation that we had before. And now we have this form, and so we can just take this and apply the chain rule. So we're going to have a 1 over lambda, which is this derivative. And then we have the derivative of h here, right? So we have first we derive the lambda, and then we derive the other h minus e. The e is not going to depend on the pi, so this part is 0. So you just have lambda, the derivative of h with respect to momentum. Now you have an h minus e here. Well, this is 0, so this part goes away, and the lambda and lambda cancel out, and so you recover that the velocity is the derivative of h and not the Hamiltonian constraint with respect of momentum. Okay? And so you do this trick, and you're going to recover all the other equation of motion that you would have by using t instead and h instead of s and the Hamiltonian constraint.
Okay. Therefore, if we set the Hamiltonian constraint equals h minus e, the affine parameter will have to be equal to time up to an arbitrary additive constant, and therefore the formulations are equivalent.
The expression above seems to imply that the Hamiltonian constraint always has to correspond to one Hamiltonian. This is not the case. Suppose we have the constraint that is the product of these two brackets, so that h1 of psi alpha is not equal to h2 of psi alpha at all points. This means that there are two regions of the extended phase space that satisfy the Hamiltonian constraints, one for h1 and one for h2. These two regions are disconnected, therefore states from different regions cannot be connected by Hamiltonian evolution. They essentially represent two different types of system encoded into the same equation. In principle, the same idea can be extended to have more than two regions.
Comment from the chat, is there maybe some more general principle like diffeomorphisms and vary that encompass all of these coordinate transformation techniques? So so these are basically all diffeomorphisms, right? But the point to me is we understand in physics what these things are doing, by looking at the component. So a lot of the time, if you just have some mathematical thing that says, oh yes, I can do a diffeomorphism here and there, but you don't understand what actually those components are doing, you lose the physics. So that's why we're looking at this in detail to understand really what the mathematical pieces are doing, so that we can better understand what and then reverse engineer what these things mean.
Okay, I think we already. While this may seem just a mathematical artifact, note that this is exactly what happens for the Hamiltonian constraint of a free particle. In fact, we can write the Hamiltonian constraint as a product where we have basically the negative and the positive energy solution. We just rewrite the square basically. Given that the solutions for energy have opposite sign, one finds that lambda is E over mc squared, in agreement with what we found before.
Note that for a free particle, similarly to what one finds in quantum field theory, we have both positive and negative energy solutions. Given that dst equals E over mc squared, what happens is the affine parameter is anti-aligned with respect to time. For the negative energy solutions then, S will be minus proper time instead of proper time. The footnote: this is a much more precise version of the claim that antiparticles traveled backwards in time. They do not. What happens is that the function t of s is parameterized in the opposite direction. However, the affine parameter s is not physically significant.
Sorry, just a question here. Does it basically mean we have two different parameterizations of the same physical solution, but we don't have two physically distinct solutions?
No, we do have two distinct solutions, but with a different parameterization. So in one solution, in one set of solution, the parameterization of the affine parameter goes in the same direction, is aligned with the direction in time. And in another set of solution, the parameterization is anti-aligned with time.
Could I just switch the parameterization of the other solution to be all the...
You can, but then you'd have a problem because let's see what's gonna happen. You are going to fail something in the Hamiltonian. You're not gonna have a one-to-one map anymore somewhere.
Okay.
Because yeah, I have to work out the map. There has to be something that for which your equation is not going to be nice and smooth anymore.
Yeah. Okay.
All right. In general, derivative of time with respect to the proper time may be positive or negative, which corresponds to the affine parameter being aligned or anti-aligned with respect to time. Note that since dt ds cannot be equal to 0, therefore the states for which that this derivative is positive can never be connected with states for which the derivative is negative. Therefore, these two types of states must always exist in different regions of the extended phase space. In analogy with what happens in quantum field theory, we call particle states those for which the derivative is positive, and antiparticle states those for which derivative is negative. We therefore find the following. A frame invariant notion of determinism and reversibility, i.e. allowing generalized coordinate transformations in Hamiltonian mechanics, gives us the notion of antiparticles even in classical particle mechanics. continue? Yes.
Alina?
Yeah.
Now that we got a better feel for what the Hamiltonian constraint is and how it works, let's go back to explore its geometry and physical significance on the extended phase space. Looking at omega AB, it may seem that adding the temporal degree of freedom means just adding another independent degree of freedom. That is not the case. We start with standard phase space and add time. We are not adding new independent configurations. If we have deterministic and reversible motion, given the state at one time, we know the state at all times. So while adding time allows us to talk about all states at all times, we are not really adding new states because states are defined and counted at equal time. In phase space extended by time only, this was captured by the fact that the form omega AB applied to the displacement field always gives 0. If we now add energy, the conjugate of time, things are even more constrained. The energy, in fact, is a function of the state of the system at a particular time. The addition of energy then adds no configurations at all. Now that it is clear that T minus E do not constitute an independent degree of freedom, we should understand the significance of the minus sign. As we saw, it was needed so that P alpha is a covector, but that does not tell us anything in terms of the geometry. What we are really saying is that an infinitesimal rectangle of size dt and dE has a negative contribution to the count of states. Should only have no contribution at all. We saw that orthogonality in phase space means degrees of freedom independence. If we have 2 independent degrees of freedom, we can write this. The above expression then can be understood as an aerial version of Pythagoras' theorem. Instead of summing the square distances, we are summing areas directly. That is, given the orthogonality of the independent degrees of freedom, we have a right triangle-like structure where the 2 sides are the areas in each degree of freedom, and the hypotenuse is the area determined by the form. Now, because spatial and temporal degrees of freedom are not independent, that is, they are not orthogonal, the form of the above expression cannot be the correct one for the temporal degree of freedom.
The naive consideration would simply be to disregard the temporal degree of freedom, since time does not contribute new states, and set does equal to just the area in phase space. However, this does not work either. This would say that the temporal degree of freedom does not identify states at all, which is not the case. Suppose we study a free particle with 1 degree of freedom. Let's assume that for t equals 0, q equals 0. We have q equals p over m and multiplied by t. And we have E equals p squared over 2m. If we look at the region where momentum is positive, the relationship is bijective. Therefore, time and energy can be used to identify and therefore count states. The issue is that those states are not new states. They are the same ones that we identified and counted by position and momentum. If we look at the expressions derived before, we have, okay.
Yeah, so when we apply the symplectic form to this displacement in position, time, and momentum and time, what you get is this minus time between the position and momentum and the time and the energy.
Okay, and we can rearrange this expression. Okay, obviously. And now compare 1.146 to 1.150. Okay.
So here
You
we
show
had
me.
then when we were applying the symplectic form to the 2 degree of freedom, we have the sum of the areas in each degree of freedom. So we have the symplectic form on this side and the areas of the first plus the area of the second. Here we have the area of the spatial degree of freedom equal the area calculated by the symplectic form plus the area in the temporal degree of freedom.
Can we, when we say a bit earlier, if we look at the expressions derived before, we have What do we mean? Do we just mean that we apply the form and that's it, or?
Right. So we already had defined the form before, right? We had it. Where was it? Here. Like we know what it is because this is the thing that actually gave us a Hamiltonian equation. Everything was working fine, right? So now we have to understand what is the physical meaning of this, right? And we can't just simply say, oh, time and energy just give us another independent degree of freedom because the state defined by time and energy are not independent from the other one. They're the same, right? So what is it that they were trying to understand? What is it that we are happening when we are writing this? Does that make sense what the question is, at least?
Pretty much, yeah.
Okay, so we saw before that the omega is basically a way to count states. So you give it two vectors and it tells you how many states you have in that little parallel pipette, right? And so what we can do here is I'm giving you two vectors, right? I'm giving you a vector that it's an infinitesimal displacement in the first position plus an infinitesimal displacement in the second position, and then a sum of two infinitesimal displacement in the two momentum, right? And then you do that, and since the only non-zero components are the one that match, you basically have this. It's the area in the first degree of freedom plus the area in the second degree of freedom. So you know that this is the thing, and this is the correct way of counting the states. And then you're going to say, okay, let's do the same thing with a displacement in a position plus a displacement in time, and a displacement in momentum plus a displacement in energy. And again, you would get the same thing, except that you have this minus E. And so the area that you have in position and momentum is, is corrected, if you want, by the areas that you're calculating in time and energy. So if you are at equal time, for example, right, then this part would not be there. You would just have this. So states at equal time, when you're defining the count of states at equal time, you recover what you had for just the position and momentum. So the question is, what are you actually doing when you have vectors that are not just that are not at equal time, right? You're basically looking at areas that sort of are shifted in time and shifting in energy. And so what we saw before is that, well, here we had the count of states is equal to the sum of the areas in the independent degrees of freedom. And here instead it's kind of the opposite. It's the area on 1 degree of freedom is the count of states plus the configuration in time and energy. And now we have to understand, what it is, and that's where the explanation is going to start.
Okay. In the second expression, the area in the spatial degree of freedom is the hypotenuse, while the area on the temporal degree of freedom and the count of states given by omega are the sides. That is why while the temporal degree of freedom and the spatial degree of freedom are not orthogonal, the temporal degree of freedom is orthogonal to the surface where states are counted. If we have a region defined at equal time, for example, the count of states reduces to the count of spatial configurations, which makes sense. In the general case, the differentials dt and dE are defined over surfaces at constant q and p, while the differentials dq and dp are defined over surfaces at constant t and e. These, as we said, are not orthogonal. This means that the area identified by dq and dp may have a non-zero projection over the temporal degree of freedom. Given that the state count should be defined at equal time, the area given by dq dp does not always properly count states. If we want the count of states to be defined at equal time, this needs to be done on the surface that is orthogonal to the surface where dt and dE are defined, which therefore forms a right triangle-like structure with the spatial and temporal degrees of freedom.
So I had some pictures from an earlier paper that I think I should have included here, but I haven't, that might give you a little bit of an intuition of what's going on. So I don't know why the text is not is so light. I don't know what happened there. I don't know if you guys can read the text there, but let me make it as big as possible so that it's easier to read. There we go. So when you have the two independent degree of freedom, this is how you can think about it. Like this is, of course, a visual representation because this thing would actually live in 4 dimension, not in 2 dimension, right? But it's still the case that essentially the area that you have in this is equal to the sum of these two. So the omega is going to be equal to the sum of dq1 times dp1 and dq2 times dp2, right? And so when you change now coordinate, what's going to happen is that this is the thing that remains invariant, and now these two things are the things that change, right? And so these two remain orthogonal to each other because they're independent degrees of freedom in phase space, and this is the count of states for that. If you go in the temporal degree of freedom, what happens is something that is more like this. The dq dp is equal to the omega plus the dt dE, right? So now this functions as the sum of the two, function as the hypotenuse. So now when you make a change of coordinates, for example, the omega is going to be the thing that remains the same, right? And your dq dp and dtt are going to be the thing that change. And if this is 0 because either dt is 0 or dE is 0, then this side will become this side, and now these two things are equal. Okay, so when we're writing, even relativity, right, the ds square is equal, the dx square minus dt square. Instead of thinking, before we had a right triangle, and now I don't know what it is because I'm not summing, instead I'm subtracting. What you should think about is that you change the role of what is the hypotenuse and what is the side. So in the first metric, you are keeping the hypotenuse the same, and you're changing the sides such that you still have a right triangle with the same hypotenuse. When you do the opposite metric, where you have a minus sign, what you're basically saying is that the metric is just one of the sides, and you're still going to have a right triangle, but what you're changing are the hypotenuse and the other side. And if you, this is something that I started doing, but I haven't finished. In a lot of diagrams where you make coordinate transformation in special relativity, if you start looking, you can actually find these triangles. And you can say, oh, I can see that this triangle is becoming the other triangle and the side is the same. And again, because this side is what really counts the states, like the states are really counted always at equal time. So if you now have a vector that it's not at equal time, well, the things that really count the states are the parts that are orthogonal to the time energy degree of freedom.
This slightly reminds me of how to say this argument for what is it? Time dilation. That basically everyone is traveling through space-time with the speed of light, and then either you are fixed in a position and then all the speed is in a temporal direction, but if you start moving in the coordinates, then okay, the time goes slower. So it's a very similar construction here, that if we start counting over the time, then okay, we need to subtract it. Yes.
Yeah. And the insight here is really that you should think about these areas that are being modified as counts of states, and those are the things that need to be invariant. And once you buy into that, a lot of those construction like start basically having a clear physical meaning, right? So the length, you can understand it as how many possible states I have there. So I might distort the length, whatever, but I still need at least the count of states is something that we agree on. And the count of states is entropy, and those are the things that are conserved in time and so on. So this is sort of a starting on inside. I think there are a lot of other things in special relativity that could be re-understood like this. And again, as always, this project, I try to get the macro pieces to get the thing going, and then there is probably a lot of stuff that can be understood even better.
I'm just wondering if this can be connected to the relativistic continuity equation.
What is the relativistic continuity equation?
Yeah, so we have for momentum, basically, yes, and we form the current by multiplying it with the density.
Oh yeah, okay.
Then it would be very similar that if we start in the
yeah, it's again, yes, because everything is about densities. So all these relationships are there because we have densities, and what we care about are the areas. So how the areas are mapped is gonna be essentially how the densities are mapped. Yeah, it's all the same thing.
Okay, I think it's my turn. The minus sign for the energy then has both a geometrical and physical meaning. If we used E instead of minus E as a variable, the minus sign would show up in the form omega AB, which would probably be better as it would make the geometrical feature more clear. However, P alpha EPI, not minus EPI, would not match the definition used in relativity, and it would not form a covector. So it would be confusing in a different way. If there is a better overall notation and grouping, we haven't yet found it. At any rate, we have found that a frame invariant notion of determinism and reversibility, i.e., allowing generalized coordinate transformations in Hamiltonian mechanics, gives elements of special relativity, i.e., energy momentum 4-vector, even without the notion of a metric tensor. What is interesting is that we didn't need to add any further assumption. dr and ind independence are sufficient. The only thing we needed to add was the ability to make generalized spacetime transformations.
So can we finish all of this? Okay, I don't think we're gonna be able to finish, especially this. Is this a good time to stop? We have like 7 minutes. I'm a little bit scared. Yeah, maybe we stop here.
Yeah, I agree. It's too detailed.
Yeah. So later we're gonna basically again regeneralize the principle of list action and all these things, and then Julius here where we're gonna find again the G alpha beta as the relationship between momentum and for velocity, so that we basically generalize what we had before. And and then we construct everything so that we can make all the things. So yeah, we should stop here. So if there are questions, we open up to questions, and otherwise we can stop before. So there was most discussion today, so we went a little bit slower, but that's fine. I mean, that's why we have this, to have the discussion.
So I've already seen like a QA somewhere, so charged particles, right? In what's coming up now. So I was just thinking about the particle-antiparticle situation
Yes.
again. And well, the antiparticle always has opposite charge, right?
Yeah.
So in the first example, there was no notion of charge. It was just a free particle, and
Correct.
momentum was just velocity times m. So
Yeah.
Particle and antiparticle are, I guess, indistinguishable because there was no charge. So in that,
Yeah.
so that's why I also had was guessing like, oh, this is just the same solution, just parameterized differently. So I wonder if we are gonna see this again, like if you're gonna see the particle antiparticle.
Yeah. So what's gonna happen is that you're gonna have forces, and the forces are gonna act exactly in the opposite way,
Okay.
and
Then
that's
they get distinct
yeah.
solutions. While
Yeah.
before they would both collapse because they are like effectively the same. Okay.
Yes. So if you only looked at the trajectories before, then I agree. If the trajectory in space, they would be absolutely the same. You wouldn't be able to distinguish. If you counted though the trajectory in phase space, so that you were counting that energy and momentum were there, then you would be able to recognize them because you have an opposite side on the energy.
Okay.
Here, instead, you are going to be able to note that they're different. I don't know if I write the equation of motion somewhere, and you're gonna no, probably I'm not writing them, but you're effectively going to see that they get an opposite force.
Yeah.
And then what's going to happen is when you change the particle in antiparticle, because you can reparameterize things and change the parameters and change the Hamiltonian constraints, so that you put a minus sign, you're going to see that effectively that is like changing the charge.
Yeah.
Right. So I haven't worked it out, but there should be a way to do some type of analog of the CPT theorem here. Right, you take the equation of motion, you change q to minus q, t to minus t, and the charge to minus charge, and then see that the equations are actually the same.
Parity would be flipping all the positional spatial coordinates, right?
Say it again.
P, the parity
T,
transformation,
yeah.
would be
Yeah,
flipping all
P
the
changes, flips the Q to minus Q.
Yeah.
T changes T to minus T,
Yeah.
and the charge would change, yeah.
Yeah.
Effective, like one way of looking at that is kind of, let's see if we can go back to these equations. Oh, I don't have them. I don't have an expressed. Yeah, I kind of don't have an expressed here, but if you imagine that you have the equation on this side, right? Putting a minus sign on the Q's and the P's, it would put a minus sign on these sides of the equation, and then also on the sides of the equation where you are looking for the change in E and in P, right? So you're putting a minus sign on each side of the equation. And then flipping the particles with antiparticles would be changing the parameterization. And so you're putting another minus sign everywhere. And so now you've put two minus signs in each of the equations, and then the equations are the same.
Yep.
That's basically like, I don't have formally done. That's something if somebody wants to play around with, it shouldn't be that hard to do. And then you basically have a much simpler understanding of the CPT theorem in classical particle mechanics, without needing all of field theory, and then you don't understand what's going on anymore. Yeah.
I just have a clarifying question.
Yeah.
In general, is Q alpha the 4 position, and then QI is the 3 position?
Yeah, so Q alpha includes time.
Okay. And then it's the zero component.
Yeah.
Okay.
And so since we are in phase space, where is it? Here we go. So, this is the TQI. This is the standard way that I would think about it. And then the P alpha is minus C with this, right? In special relativity, you typically have CT and minus E over C. Here we don't particularly need to do that because we don't need that the units or these have to be homogeneous. We basically don't care. The units can be whatever they want. But note that if you have CT times minus E over C, the C cancels out. And so you still have conjugate quantities when you have T and E, right? They're still going to be the units of phase space. So you can, when we were setting up the Hamiltonian constraint here, it's kind of easier to think of this Q0 as CT and the P0 as minus E over C, because that's what you do in relativity, but there is no need to put these C's. And then you can basically, you essentially have equations that look more, I can say, you don't have these constants around because this would be just minus E squared without the C.
Mm. Yeah.
Okay, I feel like this is a stupid question to come up with now, but like, have we like, are we actually doing special relativity? Did we say like C is like frame invariant, or are we just like using it to get the units right? Okay, we use this particular Hamiltonian constraint, right?
Right. So that's then we are not recovering. Like when we are recovering, we are going to be doing where we stopped, right? So then what we're going to basically see here, we're going to add the assumption K, right? And then we are going to have a map between P and U, right? And you see here, there's no C mentioned. What you're going to get is just that you have a metric tensor and you have these P alpha and P beta that are contracted so that you get a norm. And all of this, you see, you're doing everything without knowing that there is a C.
Yeah.
What you're going to be able to show is that whatever this thing is locally is going to be Minkowski.
Okay.
And that's about it. If C does not, the constant, yeah, you might get this constant here just because, again, you are setting this, you want a constraint that it's 0.
Yeah.
So you could say, I don't have C, but then I have my Hamiltonian constraint, it's not 0, it's something, and that something would be this number. Or you want to say, I want to set it to 0, and I want to write it such that this 1/2 matches with this 1/2, and then you're going to get this constant C squared. Right, which is basically the form momentum, like that constant is given by whatever you defined that metric to be.
Yeah. Okay.
So effectively, the C is hiding inside the metric as you would expect. You could put it in the coordinates so that the metric doesn't have it, but that's just a special choice of coordinate. In general, the C is going to be in the metric, and then depending on the coordinate, you get what you get.
Sorry, I have a question. If we could go back to Hamiltonian constraint for decoupled systems.
For the free particle, yes.
Yes.
There it is.
Or maybe a bit lower, where it was a product structure. There was H minus V1,
yes.
H, yeah, that part.
Yes.
I'm more interested in this 142. So this. So what we have here is that this is, can we interpret this as like two systems that are decoupled from each other, and they just have this, total Hamiltonian constraint of this entire big system, although these two parts are not interacting with each other?
So you can think it as two systems because once you give It's like either one is there or the other one is there. Because if I give you the state, then you know which one you have.
Yeah, so but this could also in principle be, let's say, a model of I don't know, gases that are not interacting with each other, although they're in the same environment, something like that.
No, you can't
No?
think it like that, because then you would have like either one gas or the other gas.
Huh.
Right? Because the state of the whole system is just the specification of a set of variables. And so either you have specified a set of variable and you are working in this side, right? Because this is the side that gives you the zero, or you have specified a set of variable that for which this other side gives you the zero. So it's really like you have two different Hamiltonians for the same system.
Okay, so why I'm asking is because um, since we were talking about these two distinct, I don't know, systems or universes, and then I saw this product structure. I thought this would be this could be connected to how to say, the product structure of degrees of freedom of two independent systems.
No, it's not.
It's not connected.
It's not. Yeah, it's not that.
Okay,
Like it's literally like the one Hamiltonian constraint can be mapped to multiple Hamiltonians, right? So if you have, let's say, in this case, right, you can have positive energies, and then you would be in this side of the constraint, because you would have something positive, the square root is going to be positive, and so this would be the part that is zero, and so you know that the energy is equal to this. Or you are on the other side of the constraint, the energy is negative, and then the energy is going to be minus this, because the constraint has to be zero. So either this is zero or this is zero.
So it's not even that it's like a spectrum of Hamiltonian. It's like the other way around, is that we have energy and then we can just fit whatever Hamiltonian as long as this constraint is satisfied.
Yes, correct. So in principle, it'd be fun to see whether you can chain, a set of products where you could have four Hamiltonian, right? So you don't just have like a particle and antiparticle, but then you have like some other way to differentiate. And so you have four disconnected regions of phase space. And if you are in one, you move around, you're always in that region, you can't jump to the other, right? And so basically the full state, like the system can be in these four unreachable, for zones of phase spaces that are unreachable from the other through Hamiltonian evolution.
I see. Okay, so it is quite different than what I thought. But still, let's say if I want to imagine a system where which can be decomposed into two systems with they are decoupled, but they can be formulated as let's say one Hamiltonian, although quite boring one. Would it imply anything special on Hamiltonian constraint? Not really.
I haven't thought about it, but yes, there has to be something where this product here, it probably needs to become the product of sums, so that you have it's like this Hamiltonian here has to become the sum of the two Hamiltonian for the two independent systems.
Yes, okay, additivity then, okay.
Right. And then I do not know, it's an interesting question, how you get the Hamiltonian constraint for the single system. So that part I actually do not know. Like if I have two systems, right, that each have their own Hamiltonian constraint, and therefore they map to their own Hamiltonians also. And now you put them together, but you still keep the dynamic independence, so that if you look at each decomposition, the total energy is just the sum of the two. How does that happen? Yeah, that's actually something I don't know why I never thought about looking at that. Because the interesting part, when you're putting those two things together, You could, in principle, have one description of time for one and one description of time for the other. But at some point, you need to be able to put them together, right? You need to be able to say, I'm going to use one clock for all of it, which also means that I'm going to use one energy to track the energy, the total energy. So there has to be something that then happens to the Hamiltonian constraint based on those requirements. And it's probably going to be something interesting.
Yes, indeed. I mean, if we consider, let's say, relativistic gas and I don't know, or I don't know, a fluid moving through space, and then we need to assign things such as center of mass, like some time, reference time. Which time did we choose?
Yeah, exactly.
Yeah, what is the center of mass? I mean, in general relativity is already in principle. There's no answer, or the answer is like more involved. So
yeah, exactly. So yeah. But I can see that it has to be this, because when you have a proper time, that proper time is typically the time of the center of mass of something, right? And the energy is going to be probably the energy of the total energy, again, in some similar way. So how do you go from those frames and put them together? It's probably going to be related to how do I combine the two Hamiltonian constraints.
I guess maybe in some simpler cases, I could imagine that the solution is very similar to this Einstein synchronization condition, which is basically the most symmetric one, because one can take one was drawing these signals bouncing off mirrors. One can take that these paths are of equal length, let's say, but one could also take it more twisted way where it travels all the time in one direction and then instantaneously gets back. So it's also a valid condition, but then it's not as, I don't know, intuitive, natural. So I would expect something like that, at least in flat case in Minkowski.
Yeah, so what happens, what I've found over and over with the ones who have the right math set up, the simple case just becomes simpler. So I would expect something like that to happen here, though I don't have right now a way to see it. So
okay, but yeah, I think yeah. Thanks for clarification. Yeah.
Anything else?
Just
part
of that went past me, but like coming back to, I think at some point you discussed like, what's the question? Like you have two systems, how do you create a Hamiltonian constraint for like for a two-party system or something like that?
Right. So imagine that you have, let's do something very simple. You just do standard Hamiltonian mechanics, right?
Right.
And you have two systems that evolve independently. Then in that case, the Hamiltonian is just the sum of the Hamiltonian of the two independent systems.
But for the Hamiltonian constraint, what I'm thinking about, we can have like the Hamiltonian constraint of one system multiplied by the Hamiltonian constraint of another system, and then so basically say if we have for one system the Hamiltonian is H1 and the energy is E1, so H1 minus E1 times H2 minus E2, but then also to keep like total energy the same, we multiply that by another bracket which is like total energy minus E1 minus E2. Wouldn't that work?
Well, so imagine that you have the Hamiltonian constraint like this for one system, right? And then you multiply it by another one, and now you would have H hat 1 minus E hat times H hat 2 minus E hat. Right? You take one Hamiltonian constraint, you multiply the other. At some point, you need to arrive to a case where the total thing is going to be H1 plus H hat 2, H1 plus H hat 1 minus E. because every single piece will need to see the energy is going to just be the sum of the two. So the question, how you get there. And if you just have a multiplication and you're just multiplying the two Hamiltonian constraints together, you're going to get a product of the Hamiltonian, not the sum of the Hamiltonian. So something a little bit more tricky is going to happen, which probably, like, once you find the right way to look at it, it's probably going to be so straightforward. But right now, I don't see it, right? That has to be. So clearly,
But
even this.
but if no, forget that.
Right, because even if if you go back at thinking at this as the quadratic, right? What is it? There you go. So you have the altimeter here is quadratic, and so you need to have two quadratic things, and then you put them together, and that's the quadratic of the sum of the Hamiltonian in some sense, right? How do you get there? And that has to be general enough such that you have this. In fact, now that I think about it, if you think about it, we need to get all the permutations. Because if I have a system that can be either a particle or an antiparticle, and another system that can also be a particle and antiparticle, when I put them together, I actually need 4 cases where they're both particles, where they're both antiparticle, where the first is an antiparticle, the second the particle, and the other one is opposite. So when I put together the Hamiltonian constraints, somehow I need the product of the different cases. So I don't see how it it's gonna work in some way. It's gonna work. I just don't see how it works. It's like if somebody worked it out, it's probably cute, even mathematically, see how it works. Does that make more sense, Arden?
Yeah.
Okay, so that was fun. We'll see each other next week then and continue relativity. This is a lot denser than I expected. Thank you everybody for following this. And if you do watch this afterwards, please leave a message down so that I can know that other people are watching this. And see you next week. Bye.
Bye.
Have a nice week.